Okay, here's where we left in the last video. We're gonna finish this example now. Um, we're gonna set u, we're gonna do a change of variable, and u, so we're gonna set u to be um, square root of 8t, which is the same thing as 2 root 2t. And the differential of u will be 2 times square root of 2 dt. So in order to do the substitution, dt has to be replaced with 1 over 2 root 2 du. We can just divide both sides of this equation by 2 root 2, and then that's how we obtain dt. All right, so let's put that in a bracket, indicating that is the substitution we're applying. So this s will be equal to the integral 1 over 2 square root of 2. That's going to factor out because it is a constant times the square root of 1 plus. Now, the reason why we use this substitution is because when we square u, we're going to end up with 8t squared. So u squared, and then du. We have to change the limits of integration. This is a linear substitution, which means that if t is 0, so is u. And if t is 3, then the upper limit will be 6 root 2. 6 root 2. Again, because if t is 3, we multiply that 3 with this 2, making it a 6, and we still keep the square root of 2. So those are the lower and upper limit of this integral. Okay, so now we have a constant, which is easy to handle. And now we have this, which we have to figure how to integrate. Well, we use trigonometric substitution now. So I'm going to put a new bracket. We're going to set u to be the tangent of theta, and consequently du will be the derivative of tangent is secant squared theta d theta. So we can apply the substitution. So we're going through two substitutions. First, we substitute to get 1 plus u squared, and then we substitute again. So s will be the definite integral. We're going to put the limits in a moment. Of 1 over 2 square root of 2. I keep forgetting to move this outside. It is a constant, so there's no need to keep it there. We can just put it outside of the integral. And now let's think about this. If u is a tangent, when we square it, we're going to have tangent squared. Tangent squared plus 1 is secant squared. Tangent squared plus 1 is secant squared. But then we're going to take the square root of that, so we're going to end up with secant. So this root will become secant. So secant of theta. And du is secant squared. So we have two additional secants, secant squared theta d theta. So be sure you know what is going on here. 1 plus u squared, since u is tangent of theta, is the same thing as 1 plus tangent squared, which is together secant squared. We take the square root of that. Technically speaking, we end up with the absolute value of secant. Technically speaking, we should have absolute value here. However, the numbers are going to be positive that we're going to plug in. So things are going to work out, and this secant value is going to be a positive quantity when we plug in this number. So we are good. There's no need to put absolute value because the inputs we're using work out well. So we actually have, the limits of integration. Tangent is going to be 0 when theta is 0. So the lower limit is here. And the upper limit will be the arctangent of 6 times root 2. Yep. So let me rewrite this. This S, the total length, is 1 over 2 times square root of 2, integral from 0 to the arctangent of 6 root 2 of secant cubed theta d theta. So now we have to figure this out. We're going to use a formula from calculus 2. So this is a reasonably well-known formula. So let me write this down. This is again from calculus 2. We know, so you have to go back and review it. It is probably in the section of integration by parts, where we saw that the integral of the secant cubed theta d theta, the indefinite integral, is 1/2 of secant theta tangent theta plus, this is a little long, so I'm going to continue down here, the natural logarithm of the absolute value of the secant of theta plus the tangent of theta. Close the absolute value, close the bracket, and I didn't have enough room for my constant, so I'm going to add it down here. So this is the indefinite integral formula for the secant cubed theta. It is not a bad idea to go back and review it. It should take you only 15 minutes or so to go back and review using integration by parts and also using some trigonometric identities. You also have to know, I believe, how to do the antiderivative of secant. Anyway, we know this. This is a reasonably well-known formula for the antiderivative of secant cubed. There's one more thing we need to address in the example. We have the arctangent of 6 square root of 2. It may be a good idea to draw a picture of a triangle with an angle such that the tangent of that angle gives us 6 times the square root of 2. So we can obtain other trigonometric values. So we want an angle theta so that the tangent of that angle is 6 times the square root of 2, and we can achieve that by drawing a triangle where this leg, a right triangle, where this leg is 6 root 2, this is 1. So now the tangent of this angle down here that I'm pointing to is opposite over adjacent, so 6 times square root of 2. And then if we square this quantity, we're going to end up with 36 times 2, which is 72. Again, square that, and you get square of 6, which is 36, square of the square root of 2, which is 2. 36 times 2, 72. Add 1, and we end up with the square root of 73. 36, 72, yeah, because we add 1 squared. So if we wanted to know the secant, we would have the square root of 73. So if an angle has a tangent in the first quadrant, a tangent of 6 root 2, then the secant of that same angle would be square root of 73. And the reason why we need to do this is because the antiderivative formula calls for the secant. So we're going to put square root of 73 for the upper limit of the integral when secant is used. Okay, so let's go back to S. The length is equal to 1 over 2 times square root of 2 from 0 to arctangent of 6 times square root of 2 secant cubed theta d theta. This is what we had in the last page. And so now we use that formula up here, this formula. So that is equal to 1 over 2 times square root of 2 times 1/2 I'm going to put a bracket. Secant of theta. You know what? I'm going to start plugging in these values. The formula calls for the secant of theta, which is this upper value when we are using the fundamental theorem of calculus. So the secant, as we know, is going to be the square root of 73. Tangent, well, the tangent of the arctangent of this, as long as the numbers are in the first quadrant, we have 6 times the square root of 2. So again, we're following this formula up here. 1/2, there's a 1/2. Secant, there's a secant. Tangent, there's a tangent. Plus the natural logarithm of those two numbers. This number and that number, secant and tangent. Same numbers as down here, secant and tangent. Since those two numbers are positive, there's no need to put absolute value. So we have the square root of 73 plus 6 times the square root of 2, close parenthesis. Okay. Minus, because we're using the fundamental theorem of calculus, secant of 0, which is going to be 1, times tangent of 0, we're plugging in this number, which is going to be 0, minus the natural logarithm of those two numbers, 1 and 0. Added together, 1 plus 0. They're non-negative, so there's no need to put absolute value. Close the bracket. The natural logarithm of 1, of course, is 0. And of course, that is also 0. So we end up with 1 over 4 square root of 2. And then let's consolidate those two. So that is 7 times 2 is 14, so 146. Yeah. 6 times the square root of 146 plus the natural logarithm of the square root of 73 plus, in parentheses, 6 times square root of 2. Close the parenthesis, close the bigger parenthesis, and we have it. Let me compare with my notes. Yep, that's what I got. I punched this, so this is the exact answer in all the, unless I tell you otherwise, in all the problems that I assign you for quizzes and tests, I'm going to be asking for the exact answer. That is the exact answer. I punched the numbers into a calculator, and this is about, when we plug the numbers into a calculator, about 13.32. A little less than that, 13.32. Yeah. We have established in the previous video, so this is what is going on. We want to find the actual length here, which is about 13.32. There we go. And we had mentioned in the previous video that this length of the arc has to be bigger than the straight distance across. The straight distance across is about 13.08, and we found that this length is about 13.32, which makes sense. This is longer. It is not way longer because this is a three-dimensional picture, so this is not hanging down at all. This is actually reasonably close to the straight line, not too close, but a little bit close. So we're not really going way out of our way compared to the straight line to get to that point. Yeah, and that's why the number that we obtain, the distance on the curve, is not too far off. Boy, that is very, very small when you think about it. It's about 0.24 units off if you go this way versus that way. So there we have it, exact answer. Make sure when you do your problems to hand in, you show your work. We'll stop here and before we continue with the next example in the next video.